Look up at the night sky tonight, and you'll see a tapestry of stars, swirling galaxies, and cosmic wonders stretching beyond imagination. But rewind time way back, before Earth existed, before even the stars we know today ignited, and you'd find a universe so different, it's almost alien. Picture this, a darkness so absolute, broken only by the faint glow of something barely recognizable as a galaxy. What did that very first galaxy look like? It's a question that tugs at the edges of our curiosity, a puzzle that takes us back to the dawn of everything. We're used to seeing galaxies as grand, glittering spirals or massive clusters, but the first one. It was likely a fragile, flickering thing, a delicate wisp of gas and newborn stars, barely holding itself together in a young, chaotic universe. Think of it as the cosmic equivalent of a first breath, the moment the universe began to organize itself into something recognizable. And here's the astonishing part, that first galaxy set the stage for everything that followed. Without it, there would be no Milky Way, no Andromeda, no planets, no us. This isn't just a story about distant lights in the sky, it's about our origins. Every atom in your body, every molecule in the world around you, traces back to those early cosmic structures. So how did it all begin? What forces shaped that primordial galaxy, and how did it evolve into the universe we see today? We're about to embark on a journey across billions of years, peeling back the layers of time to uncover the secrets of the first galaxy. Get ready to see the universe in a way you never have before, because this isn't just history, it's the story of us. To understand the first galaxy, we have to rewind to the very beginning, the Big Bang. Picture a moment of unimaginable heat and density, where all matter and energy in the universe burst into existence in a single, radiant instant. But here's the surprising part. Right after that explosive birth, the universe was too hot, too chaotic for anything like stars or galaxies to form. Instead, it was a swirling sea of particles, so energetic that light couldn't even travel freely. For hundreds of thousands of years, the cosmos was a glowing, opaque soup of plasma, expanding and cooling until finally, slowly, conditions changed. Then came the cosmic dark ages. With the universe cooling enough for atoms to form, light could finally travel unimpeded, but there were no stars yet to illuminate the darkness. Just an endless void filled with hydrogen and helium gas, sitting in near total blackness. This era lasted for millions of years, with gravity beginning its patient work, pulling matter together in faint, invisible clumps. And then finally the first flicker. Somewhere in that vast emptiness, pockets of gas collapsed under their own weight, igniting the very first stars. These weren't like the stars we know today. They were massive, blazing giants burning fiercely but briefly, flooding the universe with light for the first time. Those first stars were the seeds of the first galaxies. Their intense radiation and eventual explosive deaths scattered heavier elements into space, enriching the cosmic gas and setting the stage for more stars to form. Gravity pulled these stellar nurseries together, weaving them into fragile, early structures, proto-galaxies. The universe was no longer a dark, featureless expanse. Tiny islands of light began to emerge, marking the dawn of galactic history. This was the moment when the cosmic landscape shifted from simplicity to complexity, setting in motion the evolution that would eventually lead to everything we see today. Those first stars weren't just any stars, they were cosmic titans, blazing with an intensity we can hardly fathom. Scientists call them population 3 stars, the universe's very first generation. Unlike the stars we see today, these were born from nothing but pristine hydrogen and helium, the only elements that existed after the Big Bang. Without heavier elements to scatter their heat, they grew to staggering sizes, some hundreds of times more massive than our Sun. Imagine a star so colossal, it burned at temperatures 10 times hotter than the Sun, shining with a fierce, ultraviolet glare that pierced the darkness of the early cosmos. But such brilliance came at a cost. These stars lived fast and died young, their enormous mass driving nuclear reactions at a breakneck pace. While a star like our Sun can shine steadily for billions of years, population 3 stars exhausted their fuel in mere millions, a cosmic blink of an eye. And when they died, they did so spectacularly, collapsing in violent supernova that lit up the early universe like fireworks. These explosions were more than just light shows, they were the universe's first alchemists. In their fiery deaths, they forged heavier elements, carbon, oxygen, iron, and scattered them into the void. For the first time, the cosmos was no longer just hydrogen and helium. The building blocks of planets, life, and even future stars were now sprinkled across space. This was the turning point. Those heavy elements didn't just vanish, they became the raw material for the next generation of stars, cooler, smaller, and longer lived. Gravity gathered these enriched gas clouds, weaving them into denser knots where new stars could ignite. Over time, these stellar nurseries clumped together, drawn by their mutual pull, slowly taking shape as the earliest proto-galaxies. Without those first massive stars, galaxies as we know them might never have formed. They were the unsung architects of cosmic structure, their brief lives setting in motion the chain of events that would eventually lead to spiral galaxies, nebulae, and even the chemistry of life itself. So when you look up at the night sky, remember, every star you see, every planet, every speck of dust owes its existence to those primordial giants. Their legacy isn't just in the light they once cast, but in the very fabric of the universe they helped create. What exactly makes a galaxy? At its core, a galaxy is a cosmic island, a vast, swirling metropolis bound together by gravity, home to stars, planets, gas clouds, and mysterious dark matter. But the galaxies we see today, like our own Milky Way with its elegant spiral arms and bustling stellar neighborhoods, are nothing like their ancient ancestors. Those first galaxies were more like cosmic toddlers, clumsy, unformed, and far simpler in structure. Think of it this way: if a modern galaxy is a bustling megacity with skyscrapers, highways, and suburbs, then the earliest galaxies were tiny villages, just a few scattered huts connected by dirt paths. They didn't have the intricate shapes or the sheer size of their modern counterparts. Instead, they were small, fragile gatherings of stars, barely held together by gravity, swimming in vast pools of raw gas. Unlike today's galaxies, which are filled with recycled material from generations of dead stars, those first galaxies were built from pure hydrogen and helium, the only ingredients available after the Big Bang. And here's where dark matter comes in, the invisible scaffolding of the universe. Even in those early days, dark matter played a crucial role. Its gravitational pull helped gather gas into dense enough pockets for stars to ignite, acting like an unseen hand shaping the cosmos. Without it, galaxies might never have formed at all. Over billions of years, these early proto-galaxies collided, merged, and grew, feasting on gas and swallowing smaller neighbors, gradually evolving into the majestic spirals and elliptical giants we recognize today. The Milky Way, for example, wasn't born in a single moment. It's the result of countless mergers, a patchwork quilt of smaller galaxies absorbed over time. Every time you look up at the night sky, you're seeing the end product of an epic construction project that began when the universe was still in its infancy. So while those first galaxies may have been humble, they set the stage for everything that followed, including us. Astrophysicists don't just guess what the first galaxies looked like, they recreate them. Using some of the most powerful supercomputers on Earth, scientists simulate the early universe down to the smallest details, running virtual experiments that span billions of years in mere weeks. These simulations aren't just educated guesses, they're intricate cosmic time machines built on the laws of physics we've painstakingly uncovered. And what they reveal about those first galaxies is nothing short of extraordinary. Picture a supercomputer crunching numbers so vast, they'd fill libraries calculating the gravitational dance of dark matter. the turbulent flows of primordial gas, and the explosive birth of the first stars. These simulations suggest the earliest galaxies were tiny by today's standards, no bigger than a fraction of the Milky Way and far more chaotic. Instead of the elegant spirals we're familiar with, they likely resembled messy, irregular blobs, their shapes constantly shifting as they devoured gas and spawned stars at a breakneck pace. One of the most startling predictions, these proto-galaxies were stellar factories, churning out stars hundreds of times faster than modern galaxies. Without heavy elements to slow things down, star formation was a runaway process, with gas collapsing into stars almost as soon as it gathered. But this frenzy couldn't last. Those first stars, massive and short-lived, died in spectacular supernova, their explosions blasting gas outward and temporarily shutting down star formation in their infant galaxies. It was a cycle of boom and bust, a cosmic pendulum swinging between creation and destruction. Yet even in this turbulence, patterns emerged. Simulations showed dark matter acting as an invisible skeleton, its gravitational pull carving out halos where gas could pool and stars could ignite. Over time, these tiny galaxies merged, growing larger and more stable, their chaotic beginnings giving way to the ordered structures we recognize today. And while we've never directly observed one of these primordial galaxies, they're too faint and distant. These simulations give us a glimpse into a universe taking its first tentative steps toward complexity. What's remarkable is how much these virtual worlds align with the few clues we've gathered from the real cosmos. The James Webb Space Telescope, peering back to the universe's infancy, has spotted galaxies that look suspiciously like those predicted by simulations, small, faint, and brimming with young stars. It's as if the universe itself is confirming what our supercomputers have long suggested. Together, theory and observation are piecing together the story of how darkness gave way to light and how the first fragile galaxies laid the foundation for everything that followed. For billions of years after the Big Bang, the universe remained shrouded in fog, a thick veil of neutral hydrogen gas that absorbed light like cosmic quicksand. But then, something extraordinary happened. The first galaxies began flickering to life, their massive young stars pumping out torrents of ultraviolet radiation like lighthouses piercing through the mist. This was the cosmic dawn, the moment when light finally won its battle against darkness, transforming the universe forever. Picture an endless ocean of hydrogen atoms, each one capable of swallowing starlight whole. Now imagine countless newborn stars turning on all at once, their fierce UV rays blasting through that atomic sea like a storm breaking over the horizon. Each photon carried enough energy to rip electrons from hydrogen atoms, turning them from light-absorbing obstacles into transparent ionized plasma. Slowly at first, then with gathering speed, bubbles of clarity began forming around these early galaxies, patches of space where light could suddenly travel freely for the first time in cosmic history. This process, called reionization, didn't happen overnight. It was a gradual upheaval, a patchwork quilt of light spreading unevenly across the young cosmos. Some regions became transparent early, while others held onto their hydrogen fog for hundreds of millions of years longer. Eventually, though, the bubbles merged. The last stubborn pockets of neutral gas succumbed to the relentless starlight, and the universe as we know it emerged, a vast, transparent expanse where light could journey across billions of light years without obstruction. But here's what's truly remarkable. This transformation didn't just change how the universe looked, it changed how it worked. Before reionization, gravity was the dominant force shaping cosmic evolution. Afterward, light took center stage. Those UV photons didn't just clear the fog, they heated the remaining gas, making it harder for new galaxies to form in later eras. They set limits on how small a galaxy could be, effectively determining which structures would thrive and which would starve. We're seeing the aftermath of that epoch today. When astronomers point telescopes at the most distant quasars, they can actually spot the fingerprints of reionization. telltale gaps in their spectra where intervening hydrogen once absorbed specific wavelengths of light. It's like finding fossilized air bubbles in ancient ice, preserving a record of the moment when the universe took its first deep breath of transparency. The cosmic dawn wasn't just a transition, it was a revolution. It marked the point when the universe grew up, shedding its primitive, light-scattering cocoon to become the star-filled expanse we recognize. And every time we look up at the night sky, we're seeing the legacy of that transformation, the end result of photons fighting their way through the fog, lighting the path for everything that followed. For decades, astronomers peered into the depths of space with powerful telescopes, but they might as well have been staring through a keyhole. The universe's earliest galaxies remained hidden, their light stretched and dimmed by billions of years of cosmic expansion. That all changed when the James Webb Space Telescope unfolded its golden mirrors in the cold void of space. Unlike any observatory before it, Webb sees the universe in infrared light, the perfect tool for spotting those ancient, redshifted glimmers from the dawn of time. Imagine trying to read a letter that's been left out in the rain. The ink has run, the paper is faded, and whole paragraphs are illegible. That's what happened to light from the first galaxies as it journeyed across the universe. But Webb's infrared eyes cut through the cosmic smudge, revealing details we've never seen before. In its first year alone, it spotted galaxies like GLASS-z13, a faint smudge of light that had traveled for over 13 billion years before reaching us. This wasn't just another distant galaxy, it was a time capsule from an era when the universe was a mere 300 million years old, a toddler by cosmic standards. What makes Webb so revolutionary isn't just its ability to see far, it's what those distant galaxies tell us. Early theories suggested the first galaxies would be small, chaotic, and slow to form. But GLASS-z13 and others like it are surprisingly bright and well-structured, hinting that star formation in the early universe might have been far more efficient than we imagined. Some even appear to have disks, a shape we associate with more mature galaxies. This has sent astrophysicists scrambling to revise their models, wondering if the universe got its act together much faster than anyone predicted. Every image Webb captures is like peeling back another layer of cosmic history. Its infrared vision pierces through dust clouds that once obscured our view, revealing nurseries where the earliest stars were born. It spots the chemical fingerprints of heavy elements in galaxies so young they shouldn't have had time to forge them, and with each discovery, the puzzle of how galaxies grew from those first fragile sparks into the grand spirals we see today becomes a little clearer. The real magic lies in what we haven't found yet. Webb is just scratching the surface of the cosmic dark ages, and every new observation could rewrite what we know about the universe's infancy. Will we find galaxies even older than GLASS-z13? Could there be stars from the very first generation still lurking in the data? For the first time in history, we're not just theorizing about the dawn of galaxies, we're watching it play out in real time, one dazzling infrared snapshot at a time. Among the faint glimmers of ancient light captured by telescopes, one galaxy stands out as a time capsule from the universe's infancy, GN-z11. This record-breaking galaxy, observed as it existed a mere 400 million years after the Big Bang, shouldn't be this bright, this large, or this evolved. And yet, there it is, defying expectations, challenging theories, and forcing us to rethink how quickly the cosmos got its act together. What makes GN-z11 so baffling? For starters, its luminosity. This ancient galaxy shines with the brightness of a billion suns, a staggering feat for something so young. Modern galaxies take billions of years to accumulate that much starlight through gradual growth, but GN-z11 managed it in what amounts to a cosmic heartbeat. One explanation is that it must have been a stellar powerhouse, churning out new stars at a rate dozens of times faster than our Milky Way does today. Imagine a fledgling city suddenly erecting skyscrapers at impossible speed. That's the kind of frenzied activity we're talking about. But here's the twist: GN-z11 isn't just bright, it's also surprisingly metal-rich. In astronomy, metals mean any element heavier than hydrogen or helium, the building blocks forged inside stars and scattered by supernova. Finding so many metals in such an early galaxy suggests that generations of stars had already lived and died before GN-z11 took shape. It's like stumbling upon an ancient civilization and discovering they'd already invented steel, evidence that the universe's first stars worked overtime to seed the cosmos with heavier elements far earlier than anyone predicted. Then there's its structure. While many early galaxies resemble chaotic blobs, GN-z11 shows hints of a disk-like shape, something we associate with more mature galaxies that have had time to settle into orderly rotations. How did it achieve this so quickly? One theory points to a voracious appetite. Perhaps GN-z11 gorged on surrounding gas or cannibalized smaller proto-galaxies, growing rapidly while gravity sculpted its form. Another possibility is that dark matter played a role, its invisible scaffolding providing an unusually stable foundation for early growth. The real puzzle, though, is what GN-z11 implies about the universe's timeline. Its existence suggests that galaxies could form and evolve at breakneck speeds in conditions scientists once thought were too harsh, too sparse, or simply too young. If galaxies like this were common in the early cosmos, our models of cosmic dawn might need a serious rewrite. Could the first galaxies have ignited even earlier, pushing the boundaries of when starlight first pierced the darkness? Every detail we uncover about GN-z11 raises new questions. Its brilliance challenges our understanding of star formation. Its metals hint at generations of stars we've yet to detect. Its structure defies expectations of early chaos, and as astronomers comb through more data from telescopes like James Webb, GN-z11 might soon lose its title as the oldest known galaxy, not because it isn't extraordinary, but because something even older is waiting to be found. For now, this cosmic outlier remains a beacon from the past, illuminating just how little we truly know about the universe's first chapters. Dark matter is the unseen architect of the cosmos, the invisible hand that shaped the universe's very first galaxies. Unlike ordinary matter, the stuff of stars, planets, and everything we can see, dark matter doesn't interact with light. It doesn't glow, reflect, or absorb. Yet its gravitational grip is so powerful, it dictated where galaxies would form and how they would grow. Picture a vast cosmic construction site where dark matter forms the scaffolding and ordinary matter, gas and dust, simply follows its lead. In the early universe, dark matter didn't spread evenly. Tiny quantum fluctuations from the Big Bang created slight density variations like ripples in an invisible pond. Over millions of years, gravity amplified these ripples, pulling dark matter into tangled webs of filaments and dense knots known as halos. These halos acted as gravitational wells, drawing in hydrogen and helium gas like water circling a drain. Without them, gas would have remained a diffuse, featureless fog, never dense enough to ignite stars or birth galaxies. The first dark matter halos were modest, perhaps 1,000,000 times the mass of our Sun, barely large enough to cradle a few newborn stars. Today, halos like the one anchoring our Milky Way weigh 1 trillion solar masses or more, vast enough to host hundreds of billions of stars. Back then, though, the universe was smaller, simpler. Halos clustered loosely like scattered campfires in an endless night. But as time passed, they merged, growing larger and more complex through cosmic collisions. Each merger funneled fresh gas into their cores, fueling new generations of stars and stitching together the first true galaxies. Here's the twist: dark matter didn't just provide the gravitational anchor, it also set the rules for how galaxies could grow. Small halos could only hold onto so much gas before the heat of newborn stars or exploding supernova blew it away. That's why the earliest galaxies stayed petite, their growth stunted by their own turbulence. But larger halos with deeper gravitational wells could weather these storms. They retained gas, grew steadily, and eventually became the giants we see today. Modern dark matter halos are intricate tapestries woven from countless smaller ones that merged over billions of years. Simulations show them as layered structures like Russian nesting dolls with smaller subhalos orbiting within larger ones. Some of these subhalos still host dwarf galaxies, faint echoes of the universe's early days. Others remain dark, their gas long since stripped away, leaving only invisible shadows. The key to understanding galaxies, from the first flickering proto-galaxies to the majestic spirals we see now, lies in this interplay between dark and ordinary matter. One provides the gravitational blueprint, the other the luminous substance. Together, they built the universe we call home. So the next time you gaze at the Milky Way starry band, remember, what you're seeing is just the glittering surface of something far deeper, an invisible architecture shaped by dark matter's silent, ceaseless pull. Before the first stars flickered to life, the universe was a sea of pure potential, endless clouds of hydrogen and helium floating in the darkness. This wasn't just any gas, it was pristine, untouched by the heavier elements that fill our cosmos today. Without carbon, oxygen, or iron to weigh it down, this primordial mixture behaved in ways that would seem alien to modern star-forming regions. Imagine a nebula like the Orion Cloud, where dust grains act like microscopic refrigerants, helping gas shed heat and collapse into stars. Now strip away all that dust, every speck of heavier material, and you're left with hydrogen and helium alone, a gas so simple it couldn't cool efficiently. That's the puzzle the first stars faced. To form, they needed their gas clouds to collapse under gravity, but without heavy elements, those clouds had no easy way to lose heat. The only solution: grow enormous. This is why the first stars were likely monsters hundreds of times more massive than our Sun. The physics demanded it. A modern star-forming cloud can fragment into many small stars because it cools quickly, allowing dense knots to form independently. But primordial gas, stubbornly hot, resisted fragmentation. Instead, vast volumes had to collapse together, funneling enough material into a single colossal star. Picture a cosmic funnel where an entire gas cloud, light years across, pours itself into a single blazing point. The absence of heavy elements also meant these stars burned differently. Today's stars contain traces of metals that act like internal brakes, slowing nuclear reactions and extending their lives. But the first stars, pure hydrogen and helium, fused their fuel at staggering rates, their cores reaching temperatures over 100 million degrees. They were the universe's first overachievers, luminously brilliant but destined to flame out fast. Yet their brief lives were anything but quiet. When these giants finally exploded, they did so with violence unmatched by modern supernova. Some may have even collapsed directly into black holes, their deaths seeding the cosmos with the first gravitational anchors around which future galaxies would grow. More importantly, their explosions scattered the first heavy elements into space, polluting the primordial gas with carbon, silicon, and iron. This cosmic recycling marked a turning point, the moment when the universe's chemistry grew complex enough to birth smaller, longer-lived stars and eventually planets. The legacy of those pristine gas clouds lives on. Every star that formed afterward carries traces of their influence, and every galaxy bears the imprint of their chaotic beginnings. They were the crucible in which the universe's first light was forged, a fleeting era when simplicity gave way to complexity and darkness finally learned to shine. The explosive deaths of the first stars didn't just mark an end, they ignited a cosmic chain reaction that shaped galaxies for billions of years. When those massive population 3 stars reached the end of their short lives, they didn't fade quietly. They detonated as supernovae so violent, they outshone entire galaxies, blasting their guts across space in expanding shockwaves of searing gas and newly forged metals. These weren't just fireworks, they were the universe's first recycling program, turning raw hydrogen and helium into carbon, oxygen, silicon, and iron, the very ingredients future stars and planets would need to exist. But here's where things get interesting. That scattered debris didn't just float aimlessly. It collided with nearby gas clouds, compressing them like a cosmic snowplow piling up drifts. These dense, metal-rich pockets became the nurseries for the next generation of stars, smaller, cooler, and longer-lived than their massive predecessors. Unlike the first stars, which burned out in mere millions of years, these new stars could shine for billions, providing steady light and warmth to emerging planetary systems. And with each stellar death, the cycle repeated. More metals scattered, more gas compressed, more stars born. Over time, these feedback loops created a kind of galactic metabolism, an engine of creation and destruction that gradually built up galaxies' complexity. Early proto-galaxies, once little more than loose clusters of stars swimming in primordial gas, began to accumulate structure. Metals allowed gas to cool faster, collapsing into tighter knots that birthed stars more efficiently. Supernova shockwaves carved out vast bubbles in interstellar gas, creating intricate filamentary webs where new stars could ignite. Even the explosions themselves played a role in galaxy growth, their energy preventing gas from collapsing too quickly, regulating star formation like a cosmic thermostat. The legacy of this process is etched across the universe today. In the Milky Way's oldest stars, astronomers find traces of elements forged in those first supernova, ancient fingerprints of the explosions that made modern chemistry possible. And in distant starburst galaxies, where stars form at breakneck speeds, we see the same feedback loops playing out on a grand scale. The violence of stellar death isn't just destruction, it's the universe's way of building something new from the ashes. Without those early supernova, galaxies might have remained small and dim, their gas forever trapped in sluggish cycles of star formation. Instead, they grew vast and diverse, their evolution driven by the delicate balance between creation and chaos. Every spiral arm, every nebula, every planet owes its existence to those first, catastrophic explosions, the moments when dying stars lit the way for everything that followed. The first galaxies were cosmic runts, puny, disorganized, and nothing like the grand spirals and ellipticals we see today. Picture a bustling modern metropolis like New York City, then imagine its origins as a scattering of rustic cabins connected by dirt roads. That's the difference between today's galaxies and their primordial ancestors. Back then, galaxies were dwarf-sized, barely 1/10,000th the mass of the Milky Way, their stars flickering like candles in a vast, unlit void. Unlike the orderly rotation of spiral galaxies, where stars move in smooth, synchronized orbits, early dwarf galaxies were chaotic realms. Stars didn't follow neat circular paths, they jostled like bumper cars, their trajectories scrambled by frequent close encounters and the unsettled pull of surrounding gas. There were no majestic spiral arms, no glowing central bulges, just clumps of stars adrift in a sea of primordial hydrogen, their feeble gravity struggling to hold everything together. Yet these tiny galaxies had a superpower, merger potential. Alone, they were insignificant, but over billions of years they collided, sticking together like cosmic snowballs. Each merger added mass, pulling in more gas and stars, gradually sculpting something larger. Picture two raindrops merging on a window. What was once small and fragile becomes something sturdier, more complex. Now imagine that happening thousands of times across the universe, with each collision fueling bursts of star formation, churning gas into new stellar generations. Compare that to modern galaxies, where mergers still happen but on a colossal scale. When the Milky Way and Andromeda eventually collide, it won't be a chaotic smash up, it'll be a slow, stately dance between two vast structured systems. Their spiral arms will stretch and warp, their central black holes may even merge, but the sheer scale of their gravity wells means they won't disintegrate like those fragile early dwarfs. Instead, they'll likely form a massive elliptical galaxy, a smooth, featureless giant where stars orbit in all directions like a swarm of bees. The reason early galaxies were so different boils down to time and ingredients. Back then, the universe was small and crowded, with proto-galaxies packed tight like commuters on a rush-hour train. Frequent collisions kept things turbulent. Today, space is vast and galaxies are more spread out, evolving in relative isolation. Plus, modern galaxies are built from recycled material, gas enriched by generations of supernova, which cools faster and forms stars more efficiently. Those early dwarfs had to make do with raw hydrogen, struggling to ignite even a handful of stars before their gas was blown away by stellar winds. But without those scrappy little galaxies, none of today's cosmic giants would exist. They were the foundation stones of the universe, proving that even the smallest, messiest beginnings can lead to something monumental. Every spiral's whirl, every elliptical's glow, traces back to those first, unassuming clumps of stars, proof that greatness often starts small. Spotting the first galaxies isn't just a matter of pointing a telescope into the darkness, it's like trying to read a single candle flame from across an ocean. The challenges stack up fast: unimaginable distance, light stretched beyond recognition, and a universe cluttered with cosmic static. These galaxies are so far away, their light has traveled for over 13 billion years just to reach us, weakened to a whisper by the relentless expansion of space itself. That light doesn't arrive as visible starlight anymore. The expansion of the universe has stretched it into the infrared spectrum, a form of radiation invisible to human eyes and most telescopes. It's like listening to a song played at half speed. The notes are there, but they've dropped so low you need special equipment to hear them. Even then, foreground galaxies, nebulae, and even dust within our own Milky Way can obscure the view, like trying to spot a firefly through a blizzard. Enter the James Webb Space Telescope, a technological marvel designed to cut through these obstacles like a cosmic scalpel. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb specializes in infrared, the perfect tool for catching those ancient redshifted photons. Its massive golden mirror, 6 times larger than Hubble's, acts like a light bucket, gathering every possible glimmer from the edge of time. And because it orbits 1,000,000 miles from Earth, far beyond our planet's heat and light pollution, its sensors remain chilled to near absolute zero, eliminating interference from thermal noise. But Webb's innovations don't stop there. Its coronagraphs, tiny masks that block bright foreground stars, allow it to peer around cosmic glare, revealing faint galaxies hiding in the shadows. Advanced spectrographs dissect the light from these objects, revealing their composition, distance, and even the conditions under which their stars formed. It's like turning a blurry snapshot into a high-resolution biography, extracting stories from wavelengths that would have been lost to earlier telescopes. The payoff: galaxies like JWST, spotted when the universe was just 290 million years old, so young it shouldn't exist according to some models. Or the unexpected brightness of Sears 1019, defying expectations with its rapid star formation. Each discovery chips away at the mysteries of cosmic dawn, proving that with the right tools we can pull back the curtain on the universe's earliest acts. Yet even Webb has limits. The very first galaxies, those sparked by the inaugural stars, may remain out of reach, their light too dim or too redshifted for any current technology. Some could be hidden behind thicker cosmic fog, their signals absorbed by intervening hydrogen. And then there's the sheer scale of the search. Webb sees in sharp but narrow fields, like looking through a drinking straw at the night sky. Finding the rarest, oldest galaxies is still a cosmic needle in a haystack challenge, but that's what makes this era so thrilling. Every image Webb captures is a time capsule, each pixel a puzzle piece in the grand origin story of galaxies. The hurdles are immense, but so is the progress. With every observation, we're not just seeing farther, we're seeing smarter, rewriting the rules of cosmic history with every flicker of ancient light. Hidden in the depths of our cosmic backyard, there are living fossils, ancient galaxies frozen in time, preserving secrets from the dawn of the universe. Among them is Segway 1, a tiny, dim galaxy orbiting the Milky Way, so faint it was only discovered in 2006. At first glance, it's unremarkable, just a smudge of stars barely held together by gravity. But peer closer and you'll realize this isn't just another dwarf galaxy. It's a time capsule, a relic from an era when the cosmos was young, offering us a rare glimpse into what the very first galaxies might have looked like. What makes Segway 1 so special? Its stars are shockingly primitive, made almost entirely of hydrogen and helium, with virtually none of the heavier elements that fill modern galaxies. In the language of astronomers, it's metal poor, a term meaning it missed out on the chemical enrichment that came from generations of exploding stars. This suggests Segway 1 formed in isolation, untouched by the mergers and collisions that transformed most galaxies over billions of years. It's like finding a tribe deep in the Amazon that's never encountered modern civilization, a pristine survivor from another age. But the real treasure lies in what Segway 1 doesn't have. Unlike typical galaxies, it shows no signs of recent star formation. Its stellar population is old and uniform, as if the galaxy flickered to life briefly in the early universe, then simply stopped. This fits perfectly with theories about the first galaxies, many of which may have burned through their gas quickly, their star-forming potential snuffed out by supernova explosions or the harsh ultraviolet radiation of neighboring galaxies. Segway 1 could be one of these cosmic dead ends, a fossilized remnant of a time when the universe was still figuring out how to build galaxies. Studying relics like Segway 1 is like holding a piece of the cosmic puzzle that's been missing for decades. While telescopes like James Webb peer back to the universe's infancy, these nearby fossils give us a hands-on way to test our theories. They act as local laboratories, letting astronomers examine the chemistry, structure, and star formation of primordial galaxies without battling the distortions of extreme distance. And the more we find, the clearer it becomes. The early universe was a patchwork of tiny, fragile galaxies, some thriving, others stalling, each telling a different chapter of the story. Of course, Segway 1 isn't alone. Other relic galaxies like Draco Roman II and Tucana Roman II show similar traits: tiny, metal poor, and eerily quiet. Together, they form a scattered archive of cosmic history, proving that not every galaxy followed the path to grandeur. Some remained frozen in time, their evolution cut short, while others grew into the spirals and giants we know today. And that's the beauty of cosmic archaeology. Sometimes the past isn't just something we observe from afar. It's hiding in plain sight, waiting to be read in the starlight of survivors. In the chaotic nurseries of the early universe, galaxies didn't just form stars, they churned them out at a staggering, almost reckless pace. Imagine a factory operating at full throttle, its machines overheating from sheer output, except this factory spanned light years, and its product was blazing spheres of plasma. While a galaxy like ours today might birth a handful of stars each year, the infant galaxies of the cosmic dawn cranked them out hundreds of times faster, flooding the darkness with raw stellar energy. This frenzy wasn't just a matter of enthusiasm, it was physics in its purest form. Unlike modern galaxies, where star formation is a careful balancing act, early galaxies had two critical advantages: an overabundance of fresh gas and virtually no competition. Picture an endless reservoir of pristine hydrogen, untouched by previous generations of stars, stretching across the cosmos like an infinite fuel supply. Without heavy elements to regulate temperatures, this gas collapsed into stars with terrifying efficiency, like a skyscraper assembling itself in seconds. But there's another factor at play: turbulence. Modern galaxies are relatively stable places, their gas clouds calmed by magnetic fields and enriched by decades of supernova debris. In the early universe, though, everything was raw and unsettled. Gas swirled violently, clumping and collapsing in unpredictable ways, triggering chain reactions of star birth. It was like trying to light a fire in a hurricane. Once ignited, the flames spread uncontrollably. Yet this breakneck pace couldn't last forever. As those first stars burned out and exploded, their shockwaves blasted through nearby gas clouds, heating them up and pushing them apart. Suddenly, the raw material for new stars wasn't just sitting still, it was being flung outward, dodging gravity's grasp. Over time, galaxies grew more regulated, their star formation slowing from a flood to a trickle as feedback loops, supernova, radiation pressure, even growing black holes acted like cosmic governors, throttling the process down. Today's galaxies, by contrast, are models of restraint. With less gas on hand and more obstacles to its collapse, they form stars at a leisurely pace, carefully recycling old material rather than gulping down fresh supplies. The Milky Way, for example, produces about 1 solar mass of new stars per year, a crawl compared to its ancestors, and that's a good thing. If modern galaxies still operated at those ancient speeds, they'd burn through their fuel reserves in a cosmic blink, leaving behind barren husks long before life could ever take root. The difference tells a deeper story about how galaxies evolve. Early galaxies were like wild youth, splurging their resources in a blaze of energy, while modern ones are seasoned adults, balancing budgets and planning for the long term. Both approaches had their place in cosmic history, one for igniting the universe, the other for sustaining it. At the heart of nearly every modern galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational monster millions or even billions of times heavier than the Sun. But these cosmic giants didn't appear overnight. Their origins trace back to the universe's infancy, when the first galaxies were still taking shape. How did black holes grow so massive so quickly, and what role did they play in shaping their galactic homes? The answers might lie in quasars, the brightest, most violent objects in the cosmos. Quasars are the active cores of young galaxies, powered by supermassive black holes devouring surrounding gas at unimaginable rates. As material spirals inward, friction heats it to millions of degrees, unleashing blinding jets of radiation that outshine entire galaxies. In the early universe, quasars were far more common, their searing light piercing the cosmic fog like lighthouses in a storm. Some theorists argue these brilliant beacons didn't just light up the early cosmos, they fundamentally altered it. One school of thought suggests quasars acted like cosmic blowtorches, their intense radiation and particle jets heating surrounding gas, making it too turbulent to collapse into new stars. In this view, black holes were the ultimate regulators, putting the brakes on runaway star formation and preventing galaxies from burning through their fuel too quickly. Evidence comes from modern galaxies where overly active black holes often correlate with diminished star birth, but other researchers propose the opposite, that quasars actually triggered star formation. Their powerful shockwaves could have compressed nearby gas clouds, jump-starting stellar nurseries in their wake. Observations of some distant quasars show them surrounded by rings of newborn stars, as if their fury carved out fertile grounds for creation. The truth might lie somewhere in between. Early black holes likely swung between destructive and constructive phases, their influence shifting as they grew. In their youth, they may have feasted recklessly, blasting away gas and stifling star formation. But as they matured, their energy output could have become more focused, sculpting galaxy structure rather than disrupting it. Simulations show that without these black holes, early galaxies might have remained formless blobs, their gas never settling into the orderly disks we see today. There's still the puzzle of how supermassive black holes formed so quickly. Some could have grown from the collapsed cores of the first massive stars, ballooning in size as they swallowed gas and merged with others. Others might have formed directly from collapsing gas clouds, bypassing the stellar stage entirely, a process that would have created black holes thousands of times more massive than the Sun from the very beginning. Whatever their origins, black holes and galaxies seem to share a symbiotic relationship, their fates intertwined from the start. The echoes of that ancient dance linger today, written in the motions of stars, the glow of quasars, and the silent pull of darkness at the heart of every galaxy. Their story isn't just about destruction, it's about how chaos and order balanced each other to build the universe we know. Long before the universe settled into its current web-like structure, dotted with vast galaxy clusters and sprawling superclusters, the cosmos was a patchwork of scattered proto-galaxies, lonely islands drifting in the dark. But gravity is patient, relentless. Over time, the densest regions of the early universe began pulling their neighbors closer, forming the first fragile gatherings of galaxies. These proto-clusters were the primordial ancestors of today's cosmic metropolises like the Virgo cluster or Coma supercluster, but they couldn't have been more different. Imagine a fledgling town springing up where only farmsteads once stood. The earliest galaxy clusters weren't the dense, glittering hubs we see now. Instead, they were loose associations, bound by tentative gravitational handshakes, their member galaxies still mostly gas-rich and unrefined. Simulations suggest these structures emerged shockingly early, perhaps just 1 or 2 billion years after the Big Bang, when the universe was less than a fifth of its current age. Some, like the recently discovered protocluster around the galaxy cosmos as TC31, show dozens of young galaxies crammed into a space just a few million light-years across, already hinting at the gravity-driven mergers that would one day forge true clusters. Compare that to modern titans like Virgo, a bustling galactic city spanning 10 million light-years and housing thousands of galaxies, where Virgo's core is dominated by massive elliptical smooth, featureless giants that have cannibalized their neighbors over eons. Ancient protoclusters were chaotic construction zones, filled with irregular galaxies still birthing stars at breakneck speeds. Virgo's galaxies are largely quiet, their gas supplies depleted by collisions or stripped away by the cluster's searing hot plasma. But in the early universe, clusters resembled fireworks factories, alive with the pops and flashes of supernova and colliding gas clouds. The differences don't end there. Today's galaxy clusters sit at the intersections of cosmic filaments, drawing in new members from surrounding voids like water draining into a sinkhole. But proto-clusters were more isolated, adrift in a universe that hadn't yet fully carved out its large-scale structure. Their growth was messier, driven less by orderly infall and more by brute force collisions between neighbors. Some may have even been strangled in their youth, their gas supplies blown away by fierce radiation from nearby quasars before they could mature into true clusters. Yet despite their chaotic origins, these early gatherings set the stage for everything that followed. The same gravitational tugs that first drew galaxies together continue shaping the universe today, just on a grander scale. Every cluster, from the tiniest groups to the mightiest superclusters, owes its existence to those tentative first steps, a reminder that even the largest structures in the cosmos started small. The universe keeps meticulous records not in books or stone but in starlight itself. When astronomers peer at the light from ancient galaxies, they're not just seeing brightness and color. Hidden in that glow are chemical fingerprints, subtle signatures that betray the presence of elements forged in stars long gone. It's like finding smoke lingering in the air long after a fire has burned out, proof of something powerful that once existed, even if we can't see it directly. This detective work hinges on spectroscopy, a technique that splits light into its constituent wavelengths, revealing dark lines where specific elements have absorbed certain colors. When applied to galaxies like GN-z11, dating back to the universe's infancy, the results are startling. Despite their extreme youth, these galaxies already show traces of oxygen, carbon, and neon elements that couldn't have formed in the Big Bang. Their presence is a smoking gun, evidence of an even earlier generation of stars that lived fast, died violently, and salted the cosmic landscape with their remains before vanishing without a trace. These ghostly ancestors, known as population 3 stars, left behind no direct light for us to observe. Their brief, brilliant lives ended billions of years before even the oldest galaxies we can spot. But their legacy lingers in the chemistry of later stars. Think of it like baking a cake. Once you've stirred in sugar, you can't see the individual grains anymore, but their presence transforms the whole mixture. Those first stars were the universe's bakers, mixing heavy elements into the primordial gas that would eventually form the stars we can see. The real surprise is how quickly this enrichment happened. Some of the oldest known galaxies already show metal levels a tenth of our Sun's, far more than expected, if only a few population Roman 3 stars had existed. This suggests those first stars weren't rare loners, but numerous enough to pollute vast swaths of space in just a few million years. Their combined explosions must have been a cosmic fireworks show unlike anything since, seeding the universe with the raw materials for planets, life, and everything that came after. Modern telescopes like James Webb are turning these chemical whispers into shouts. By analyzing the spectra of extremely distant galaxies, astronomers can now map how different elements were distributed across space and time. Some regions show unexpected pockets of heavier elements, hinting at especially intense bursts of early star formation. Others reveal peculiar ratios like too much oxygen compared to iron, that suggest certain types of supernova dominated the early cosmos. Each measurement is another brushstroke in a portrait of an era we can't observe directly, but whose influence surrounds us in every atom. So while we may never glimpse a population Roman 3 star directly, their presence is written into the fabric of the universe itself. Every time astronomers detect carbon in a distant quasar or measure silicon in an ancient galaxy, they're reading the last will and testament of those vanished giants. Their atoms now form planets, oceans, even the cells in our bodies, making those first stars not just ancient history but part of us all. For decades, the story of galaxy formation seemed straightforward. Gas cools, stars ignite, gravity pulls everything together. But what if the universe had shortcuts? Some theorists propose radical alternatives, like galaxies sprouting not from starlight, but from the sudden collapse of primordial gas into massive black holes, skipping stars entirely. Imagine a cosmic cheat code where giant gas clouds, heated by ultraviolet radiation or compressed by dark matter, bypass the stellar phase and implode directly into black holes weighing thousands of suns. These so-called direct collapse black holes could have served as instant anchors for early galaxies, their gravity pulling in surrounding gas before the first stars even had a chance to form. Others suggest dark matter, usually seen as a passive scaffold, might have played a more active role. Certain models propose hypothetical dark stars, theorized objects powered not by nuclear fusion but by dark matter particles annihilating at their cores. These exotic structures could have grown to staggering sizes, their gentle glow replacing the violent blaze of early stars and altering how galaxies assembled. Then there's the idea of cosmic strings, hypothetical defects in spacetime left over from the Big Bang acting as gravitational zippers, gathering gas along their lengths to form galaxy-forming filaments in ways standard physics can't explain. Despite their creativity, these ideas remain on the fringes. The mainstream view, backed by overwhelming observational evidence, still favors the gradual buildup of galaxies through stellar births and mergers. Yet exploring these alternatives isn't just academic whimsy, it's a pressure test for our theories. By probing how galaxy formation might have unfolded differently, we better understand why it unfolded the way it did. Sometimes the most illuminating questions aren't about what happened, but what almost happened, and why the universe chose one path over another. The existence of ultramassive black holes in surprisingly young galaxies, for instance, keeps the direct collapse theory alive as a possible explanation for cosmic oddities that don't fit the standard timeline. What unites all these theories, mainstream or not, is the recognition that the early universe was a laboratory of extremes, a place where the rules we take for granted today might have bent or even broken. Whether through dark stars, cosmic strings, or something stranger still, the story of galaxy formation remains an open book, with some of its most intriguing chapters yet to be written. Simulating the birth and evolution of galaxies isn't just guesswork, it's a feat of digital alchemy. At research centers worldwide, supercomputers hum with trillions of calculations, reconstructing the universe's history in silico. Projects like JWST aren't mere animations. They're virtual universes governed by real physics, where dark matter, gas, and stars interact with startling realism. Picture feeding Einstein's equations into a machine alongside data on cosmic expansion, then pressing play to watch 14 billion years unfold in weeks. This is how we test theories too vast for labs and eras too distant for telescopes. Take JWST's latest run, a cube of simulated space spanning 1 billion light-years. Inside, dark matter weaves its invisible web, while hydrogen gas swirls into filaments, pooling at intersections where galaxies ignite. The simulation tracks everything from supernova explosions stripping gas from dwarf galaxies to black holes belching jets that sculpt entire clusters. What emerges isn't just pretty visuals, it's a dynamic blueprint of cosmic evolution, matching actual galaxy surveys with uncanny precision. When astronomers point telescopes at the Virgo cluster, they find galaxies distributed much like JWST predicted, evidence that the code has captured something fundamental about reality. Yet these simulations also reveal surprises. One shocker: early galaxies might have grown faster than previously thought. By tweaking variables like gas cooling rates and star formation thresholds, researchers found certain conditions could produce massive galaxies alarmingly young, a hint that the real universe had cosmic shortcuts we're only beginning to understand. Another insight involves magnetic fields. JWST's models show how primordial magnetism, stretched and twisted by galaxy collisions, could amplify to the strength observed today, solving a puzzle that stumped astronomers for decades. The devil and the discovery lies in the details. For instance, JWST's galaxies develop realistic spiral arms not because programmers hand drew them, but because the simulation's physics naturally generates instabilities that whirl gas into these structures. Even the metallic fingerprints of stars, their chemical abundances, emerge organically as supernova pollute virtual gas clouds between generations. It's a self-contained cosmos evolving by rule rather than fiat. But these digital universes aren't flawless. They struggle to simulate the smallest scales, like individual star-forming clouds, forcing simplifications that might skew results. Some critics argue simulations risk becoming cosmic horoscopes vague enough to predict almost anything. That's why projects like Fire and Eagle take different approaches, testing how varying assumptions about feedback or dark matter alter outcomes. Discrepancies between models and observations, like the too big to fail problem where simulated dwarf galaxies appear more massive than real ones, keep theorists honest, driving refinements. What's breathtaking is how these tools bridge eras. By rewinding simulations to moments like the cosmic dawn, scientists can test whether observed anomalies, say a bizarrely bright early galaxy, fit standard theories or demand new physics. It's like having a time machine where you can rerun the universe's first chapters with different settings, asking, "What if?" at every turn. As supercomputers grow more powerful and codes more sophisticated, these virtual cosmos inch closer to mirroring reality, not just reflecting what we see, but revealing the hidden laws that shaped it. The hunt for the universe's first galaxies is far from over. In fact, it's just getting started. Right now, Telescopes like James Webb are rewriting the cosmic rulebook, but the next generation of observatories promises to push even further, peering deeper into the past than we ever thought possible. Take NASA's Nancy Grace Roman Space Telescope, set to launch in the late 2020s. While Webb zooms in on distant galaxies with unmatched precision, Roman will survey vast swaths of sky, acting like a cosmic census taker. Its wide-field infrared camera could spot hundreds of primordial galaxies in a single sweep, revealing patterns in their distribution that hint at how the earliest structures emerged from the darkness. But the real game-changer might be the Extremely Large Telescope, or ELT, currently under construction in Chile's Atacama Desert. With a mirror spanning 39 meters, nearly 4 times wider than Webb's, this ground-based giant will have the light-gathering power to detect some of the faintest, most distant objects ever glimpsed. What sets ELT apart is its ability to study the chemical makeup of these ancient galaxies in unprecedented detail. Imagine analyzing the atmosphere of a planet orbiting a star in one of the universe's first galaxies, a feat that could soon be within reach. Then there's the ambitious LUVOIR concept, a proposed space telescope with a mirror up to 15 meters across. If funded, it could directly image Earth-like planets in systems dating back to the cosmic dawn, while also capturing the faint glow of the very first stars as they ionize the primordial fog. Combined with gravitational wave detectors like LISA, which might sense mergers of the earliest supermassive black holes, we're on the verge of assembling a multisensory portrait of the universe's infancy. What could these instruments find? Theories abound. Some predict a hidden population of ultra-faint dwarf galaxies, too dim for current telescopes but crucial to understanding how structure formed. Others speculate about dark galaxies, clumps of gas and dark matter that never ignited stars, lurking like cosmic ghosts. There's even the tantalizing possibility of spotting population Roman III stars themselves, not just their aftermath. If any of these first-generation giants formed in isolation, surviving longer than their short-lived peers, ELT or LUVOIR might catch their dying light. The most exciting prospect, discovering something no theory predicted. Every time we've built a more powerful telescope, the universe has handed us surprises, galaxies where none should exist, black holes too massive for their age, chemical abundances that defy explanation. The next chapter of first galaxy hunting won't just fill in gaps. It could rip up the textbook entirely, revealing a dawn of time stranger and more spectacular than we ever imagined. One thing's certain, the closer we get to the Big Bang, the more the cosmos reminds us how much we still have to learn. With each new observatory, we're not just building better tools, we're opening windows to eras when the universe was still figuring itself out, watching as the first sparks of structure flicker to life in the darkness. And somewhere in that ancient light, the answers to our biggest questions are waiting. Sci-fi loves to dress up ancient galaxies as cosmic superpowers, glittering utopias or dystopias where hyper-advanced civilizations wield godlike technology. Think of the Ori from Stargate, their galaxy-spanning empire tapping into energy sources that blur the line between science and magic. Or Marvel's Celestials, towering cosmic architects who supposedly seeded life across the universe billions of years ago. These stories are thrilling, but the reality of the first galaxies, far less polished and far more fascinating. Real ancient galaxies weren't gleaming metropolises humming with alien megastructures. They were scrappy, messy, and barely holding themselves together. Picture a cosmic junkyard instead of a celestial palace, clouds of gas clumping into unstable knots, stars igniting and exploding in chaotic bursts, and fragile structures prone to collapsing under their own turbulence. No celestial overlords, no grand designs, just raw physics playing out on a scale we're still struggling to comprehend. That's not to say pop culture always gets it wrong. Some depictions nail the eerie, primordial vibe. The rebooted Battlestar Galactica hinted at a cyclical universe where civilizations rise and fall over cosmic timescales closer to the truth that galaxies are born, evolve, and sometimes collide or fade. Even Star Trek occasionally dips into realism, with episodes referencing proto-galaxies as volatile stellar nurseries rather than polished empires. And let's not forget Contact, where the alien signal's origin point, a distant, ancient source, mirrors how astronomers actually trace radio waves back to early galactic activity. The biggest myth sci-fi perpetuates, that ancient equals advanced. In reality, the first galaxies were cosmic toddlers, inexperienced, unstable, and chemically primitive. They lacked the heavy elements needed for planets like Earth, let alone hyperdrives or dimensional portals. Their brilliance came from sheer energy, not sophistication. Imagine comparing a wildfire to a nuclear reactor. One's raw and untamed, the other precise and engineered. The first galaxies were the wildfire, yet there's a poetic truth hidden in the fiction. The awe these stories evoke isn't entirely misplaced. Those early galaxies were extraordinary, not because they hosted civilizations, but because they lit the fuse for everything that followed. Every star, every planet, every ingredient for life owes its existence to those chaotic beginnings. So while the Ori might make for better TV, the real origin story of gas, gravity, and time is the ultimate epic. And the best part, we're still uncovering its twists. Studying the first galaxies isn't just about mapping cosmic history, it's a mirror held up to our own existence. Every atom in our bodies, every breath of oxygen we take, was forged in the hearts of stars that formed from the ashes of those primordial giants. When astronomers peer back to the cosmic dawn, they're not just collecting data, they're tracing a lineage that connects us directly to the infancy of the universe. Carl Sagan once said, "We are a way for the cosmos to know itself, and nowhere is that truth more palpable than in the hunt for our galactic origins." This pursuit carries a quiet humility. The light we're capturing from galaxies like GN-z11 has traveled for over 13 billion years, a span so vast it dwarfs all of human civilization into insignificance. In those faint photons, we're not just observers but participants in a story that began long before Earth existed. Astronomer Michelle Thaler puts it beautifully. When you look at the oldest light in the universe, you're not seeing it as it is now. You're seeing it as it was when the universe was still figuring out what it wanted to be. There's a profound resonance in that idea. We're glimpses in a cosmic reflection, temporary but essential stitches in the fabric of time. Yet with this knowledge comes responsibility. The same telescopes revealing our cosmic ancestry are also uncovering unsettling truths. Those early galaxies formed in a universe far denser, far more chaotic than our own, a reminder that our tranquil corner of space is the exception, not the rule. As astrophysicist Katie Mack notes, we're living in the afterglow of creation, in a fleeting pocket of stability. The more we learn about the violent, turbulent beginnings of galaxies, the more fragile our own existence seems. It's no accident that so many astronomers describe their work as existential meditation. Each discovery is a double-edged sword, filling us with awe while underscoring our impermanence. But there's another layer here, beyond humility or fragility. Studying the first galaxies is an act of defiance against cosmic forgetfulness. Those early stars died without witnesses, their light fading into darkness long before eyes existed to see it. By reconstructing their stories, we're giving meaning to events that would otherwise be lost to time. In a universe that forgets, science remembers. Every spectrum analyzed, every simulation run is a rebellion against entropy, a way of saying, this mattered. Perhaps that's the deepest ethical weight of this work. We're not just decoding the past, we're asserting our place in a continuum that stretches from the Big Bang to this very moment. Neil deGrasse Tyson often speaks of the cosmic perspective, the realization that we're not just in the universe but of it. When we study the first galaxies, we're not distant scholars poring over ancient texts. We're children finally old enough to read our own origin story written in starlight and shadow, and like all great stories, it changes those who hear it. The universe began in fire and chaos, spent billions of years building complexity, and somehow against all odds produced beings capable of understanding it. That's not just science, that's poetry written in the language of physics. All right, time for a cosmic challenge. Let's play Name That Galaxy. Here's how it works. I'll show you 3 real images captured by Hubble and the James Webb Space Telescope, each featuring a galaxy that could be one of the oldest ever observed. Your job, guess which one you think takes the title of most ancient. Don't worry, I'll reveal the answer later. No peeking ahead. First up, meet candidate number 1. A faint reddish smudge in the constellation Ursa Major. At first glance, it looks unremarkable, like a speck of dust on a camera lens. But that red hue is a giveaway. It's light stretched by the expansion of the universe, a sign this galaxy's photons have been traveling for over 13 billion years. What's wild is how small it appears, no majestic spiral arms, just a hazy blob. Yet inside that blur, stars were being born at a rate that would put our Milky Way to shame. Now candidate number 2, this one's a bit brighter with a slightly more defined shape. You can almost make out a central glow surrounded by fragmented clusters, like a broken necklace of stellar fire. What's intriguing here is the presence of heavier elements, oxygen and carbon, detected in its light spectrum, hinting that it might be a second-generation galaxy, already enriched by the explosions of earlier stars. But don't let that fool you. Age isn't always about purity, sometimes it's about timing. And finally, candidate 3, a chaotic, asymmetrical knot of light, more splatter than structure. This one's surrounded by what looks like a faint halo, possibly the glow of ionized gas blasted by newborn stars. It's the messiest of the trio, but that turbulence might be the key to its age. In the early universe, galaxies didn't have the luxury of neat, orderly rotations. They were raw and unruly, just like this. So which one's the oldest? If you guessed candidate 1, the tiny red smudge, you're close but not quite right. Turns out it's actually candidate 3, the chaotic knot. Here's why. While the red galaxy is incredibly distant, its light shows traces of metals, meaning it isn't part of the very first wave. That messy third candidate, though, its light profile matches simulations of galaxies forming in pristine gas, untouched by prior generations. Sometimes cosmic youth looks more like a toddler's finger painting than a masterpiece. The real takeaway: age in the cosmos isn't always what we expect. The oldest galaxies aren't necessarily the dimmest or the smallest. They're the ones carrying clues of a time before recycling, before order, when the universe was still figuring out how to build something from nothing. And every time we spot one, it's like finding a fossilized whisper from the dawn of everything. Behind the glow of computer screens in observatories around the world, a quiet kind of magic happens long after midnight. Picture an astronomer hunched over a keyboard, caffeine-fueled and squinting at spectral data that's just arrived from a telescope millions of miles away. The numbers on the screen could be noise, or they could be the faint whisper of a galaxy so old it predates most of cosmic history. This is where breakthrough moments are born, not in polished press conferences, but in the bleary-eyed hours when the rest of the world is asleep. Take Dr. Jane Rigby, an astrophysicist who worked on the James Webb Space Telescope. One night, as she sifted through early test data, her team spotted an anomaly, a strange spike in the infrared readings. For a heart-stopping moment, they feared a critical instrument flaw. Then the realization hit: they weren't seeing an error. They were catching their first glimpse of redshifted light from an ancient galaxy, its signal so stretched by cosmic expansion that it appeared in wavelengths no human eye could see. That midnight eureka, a moment, became the foundation for discoveries that would later make headlines worldwide. But not all nights end in triumph. Sometimes it's a battle against glitches, like the time Chile's ALMA radio telescope went offline during a crucial observation window, leaving astronomers scrambling to debug frozen servers while a distant quasar slipped from view. Or the graduate student who spent weeks tweaking code to remove artifacts from deep field images, only to realize the noise was actually a cluster of dwarf galaxies hiding in plain sight. Science at this level is equal parts persistence and poetry, a dance between raw data and human intuition. The pressure is relentless when competing teams are racing to confirm the same distant galaxy. Every minute counts. One researcher described the scramble to publish before a rival group as astronomical poker, where you're weighing whether to hold out for more data or go all in with what you've got. The stakes credit for discoveries that redefine textbooks, yet even in this high-stakes environment, camaraderie thrives. It's not uncommon for astronomers across continents to share troubleshooting tips over midnight Zoom calls, united by the thrill of chasing light from the edge of time. What keeps them going? It's those rare moments when the universe winks back, like when a postdoc at Mauna Kea noticed an odd fluctuation in a dataset and after 3 sleepless nights confirmed it as the chemical signature of a first-generation star. Or the team that high-fived over coffee-stained notebooks when their simulation finally matched a real galaxy's weirdly skewed shape. These aren't just data points, they're handshakes across billions of years, proof that human curiosity can bridge the unimaginable gulf between our world and the cosmos's dawn. And sometimes the magic happens in the unlikeliest places, like the professor who cracked a stubborn modeling problem during his toddler's 2 a.m. bottle feeding, scribbling equations on a napkin. Or the undergrad who spotted an error in a renowned team's calculations while reviewing notes on a delayed subway ride home. The search for the first galaxies doesn't just belong to telescopes, it lives in the quiet, dogged moments when ordinary people refuse to let the universe keep its secrets. Science thrives on surprises, and the study of early galaxies has delivered some of the most jaw-dropping curveballs in modern astronomy. Take GN-z11, that record-breaking galaxy we mentioned earlier. It wasn't just old, it was bafflingly bright, shining with the luminosity of a billion suns when the universe was barely a toddler. This wasn't supposed to happen. According to most models, galaxies that young should have been small, dim, and chaotic, not these radiant beacons defying the cosmic rulebook. The discovery sent theorists back to their chalkboards, scrambling to explain how structures could mature so quickly in what was supposed to be a sparse, unorganized universe. Then came Webb's knockout punch, galaxy clusters like the one around the quasar J0100+28, dating back to when the universe was only 600 million years old. These weren't just lone overachievers. They were fully fledged communities, galaxies clustering together far earlier than anyone predicted. Simulations had painted the early cosmos as a loose scattering of isolated proto-galaxies, like lone campfires in a vast wilderness. But Webb revealed bustling galactic townships, hinting at a cosmic social network forming at breakneck speed. The implications ripple across astrophysics. Did dark matter clump faster than we thought? Did some unknown physical process turbocharge galaxy growth, or are we missing a fundamental piece of the puzzle altogether? Perhaps the biggest head-scratcher is the metal problem. Early galaxies like Sears 1019 shouldn't have been so chemically enriched. Heavy elements like oxygen and carbon are forged in stellar furnaces and scattered by supernova, a process assumed to take generations. Yet here were galaxies, observed in the universe's first few hundred million years, already sporting elemental cocktails resembling modern stars. It's like digging up a medieval castle and finding steel beams inside, evidence that the universe's first stars worked overtime, seeding the cosmos with heavy elements at a pace that still isn't fully understood. These surprises aren't just academic curiosities, they're reality checks. Every time a telescope like Webb overturns expectations, it's a reminder that the universe doesn't care about our models. The cosmic dawn wasn't a tidy, predictable transition. It was a messy, improvisational era where galaxies experimented with forms and growth spurts we're only beginning to catalogue. And that's the thrill of it all. For every question answered, a dozen new mysteries emerge, keeping the story of our origins alive with possibilities. Ever wish you could be part of cutting-edge astrophysics without needing a PhD or access to $1 billion telescope? Here's the best-kept secret in science: you absolutely can. Thanks to citizen science projects, anyone with an internet connection can help astronomers unravel the mysteries of the cosmos, including hunting for galaxies so ancient they've never been seen before. It's like having a backstage pass to the greatest discovery show in the universe, and all you need to bring is your curiosity. Take Galaxy Zoo, for example. This groundbreaking project lets you roll up your sleeves and classify real galaxies from telescope images. Here's how it works. You're shown a snapshot of a galaxy, maybe a spiral with elegant arms, a blurry elliptical blob, or a weird, irregular shape that defies categories. With a few clicks, you tag its features, and just like that, you're contributing to research that could rewrite textbooks. The magic: computers still struggle to spot subtle patterns in galaxy shapes, but the human brain excels at it. In fact, volunteers have discovered entirely new classes of galaxies, like the whimsically named green peas, a small, glowing clusters crucial to understanding star formation. But Galaxy Zoo is just the beginning. Projects like Zooniverse host dozens of astrophysics initiatives where amateurs routinely make headlines. There's Backyard Worlds Planet 9, where participants scour telescope data for hidden objects at the edge of our solar system. Or Hubble Asteroid Hunter, where eagle-eyed volunteers spot space rocks photobombing deep space images. One retiree in Germany even found a supernova, a stellar explosion, while sipping coffee at his kitchen table. These aren't just feel-good stories, they're proof that discovery isn't limited to labs or observatories. If you're craving even more hands-on involvement, platforms like SETI at Home let you donate your computer's idle time to crunch radio telescope data, searching for alien signals in the cosmic static. Or dive into Cosmic Dawn, a project simulating early galaxy formation where your home PC helps astrophysicists test theories about the universe's first structures. It's like running a mini supercomputer from your couch. The beauty of these projects isn't just their accessibility, it's their impact. When thousands of eyes scan the same data, anomalies stand out faster. A teacher in Australia once flagged a strange flicker in galaxy images that turned out to be a rare black hole eruption. A student in India noticed an odd color gradient in a distant nebula, leading to a paper on chemical enrichment in early stars. These breakthroughs don't happen despite amateur involvement, they happen because of it, and the best part, you don't need prior knowledge. Training tutorials walk you through every step, and online communities buzz with enthusiasts swapping tips. Whether you spend 5 minutes or 5 hours, each contribution nudges science forward. So the next time you gaze up at the night sky, remember, those distant galaxies aren't just points of light. They're puzzles waiting to be solved, and you might be the one to crack them. 13.8 billion years ago, the universe burst into existence as a seething, formless soup of energy. Fast forward 400,000 years, and the first atoms, hydrogen and helium, condensed from the cooling chaos like dew on a cosmic leaf, but true structure wouldn't emerge for millions of years. Imagine the universe at 500 million years old. A vast darkness punctuated by flickering embers, population, 3 stars igniting in the gravitational wells of dark matter. These stellar pioneers lived fast and died young, scattering the first heavy elements into the void like cosmic confetti. By 700 million years, their ashes coalesced into the first proto-galaxies, delicate wisps of stars and gas, no larger than 1% of the Milky Way's mass. Picture them as cosmic toddlers stumbling through a playground of hydrogen, colliding and merging in slow motion. Around 1 billion years, something extraordinary happened: reionization. Those early galaxies, brimming with hot young stars, flooded the universe with ultraviolet light, burning away the hydrogen fog like morning sun burning off mist. The cosmos became transparent, and the stage was set for grander structures. 2 billion years in, galaxies began clustering, drawn together by dark matter's invisible threads. The Milky Way's ancestors were among them, dozens of dwarf galaxies swirling in a gravitational dance. By 5 billion years, these fragments had merged into a recognizable spiral, its disk taking shape as gas cooled and settled into a rotating plane. But the Milky Way wasn't done growing. Over the next 8 billion years, it cannibalized smaller neighbors, including the Gaia-Enceladus galaxy, whose stars still orbit as a fossilized stream in our halo. Today, 13.6 billion years after the Big Bang, our galaxy spins with 200 billion stars, its spiral arms tracing the echoes of ancient collisions. Yet the timeline isn't just about scale, it's about chemistry. Those first galaxies held only hydrogen and helium. Now, the Milky Way's gas is laced with carbon, oxygen, iron elements forged in stellar hearts, and supernova blasts recycled across generations. Every atom in your body, from the calcium in your bones to the iron in your blood, was crafted in this galactic alchemy. What's next? In 4 billion years, the Milky Way will collide with Andromeda, birthing a new elliptical galaxy, Milkomeda. Stars will scatter like sparks from a firework, though so few will collide that the night sky will still seem familiar to any survivors. But that's a story for another era. For now, we're suspended in a golden age of cosmic observation, piecing together our galaxy's epic biography, one ancient star, one relic stream, one infrared photon at a time. So here we are at the edge of cosmic understanding, looking back at those first flickering galaxies that set the universe alight. They weren't the grand spirals we know today, but fragile, chaotic things, clusters of stars barely held together by gravity, swimming in seas of pristine gas. These were the pioneers, the ones that burned bright and fast, scattering the first heavy elements into the void like cosmic seeds. Without them, there would be no Milky Way, no Earth, no us. Think about that for a second. Every ingredient that makes up our world, the oxygen in our lungs, the iron in our blood, was forged in those early stellar furnaces and scattered across space by supernova. Those first galaxies didn't just light up the darkness. They built the very foundation of everything that came after. They kicked off reionization, clearing the cosmic fog and transforming the universe from an opaque sea of hydrogen into the transparent expanse we see today. Yet for all we've uncovered, the story is far from complete. How did those early proto-galaxies grow so quickly, defying our models? What role did dark matter truly play in shaping them? And where, if anywhere, can we find the elusive population Roman 3 stars, the universe's very first generation, whose existence we've only inferred from chemical echoes? These aren't just academic questions, they're keys to understanding our own origins. The beauty of astronomy is that it's a field in motion. Every new telescope, every fresh observation peels back another layer of cosmic history. With instruments like James Webb and the upcoming extremely large telescope, we're not just searching for answers, we're rewriting the questions, so stay curious. Keep looking up, because the universe's first chapters are still being decoded, and the next groundbreaking discovery might be just one observation away. Who knows, the next time you gaze at the night sky, you might be staring at a corner of the cosmos no one's ever truly seen before. And just like that, we've traveled across billions of years, from the first flickers of starlight to the grand galaxies we see today. But here's the thing, this story isn't finished. Every time we peer deeper into space, the universe surprises us, and that's where you come in. What do you think the very first galaxy looked like? Was it a fragile wisp of stars barely clinging together, or something stranger, something our telescopes haven't spotted yet? Drop your theories in the comments. I read every single one, and who knows, your idea might just spark the next big debate. If you love this cosmic deep dive, don't forget to smash that like button and subscribe. Why? Because we're just getting started. Up next, we're tackling an even wilder question. Could alien life have existed in those ancient galaxies? Imagine civilizations born under the light of the universe's first stars. What would they have been like? The answer might shock you. Hit subscribe so you don't miss it. Until then, keep looking up, because the night sky isn't just full of stars. It's full of stories waiting to be told.